This device is called a Jacob's ladder. And this is a really noisy display in a science center somewhere up in New England. That's called a Van de Graaff generator. These are, of course, both displays of the power of electricity. Want to see a really serious display of the power of electricity? Take a look at this. That's what electricity can do. But of course, electricity is also responsible for the fact that you're watching this right now. And that's because of something called electric charge. And this is kind of the beginning of our discussion of electric charge. Most people already know by the time you get around to a physics video that electric charge comes in two types. They are called positive and negative, and they were named by, of all people, the American Ben Franklin. You remember him, revolutionary hero, inventor of the post office and bifocal lenses. There's a picture of Ben right there, one of our country's founding fathers. Excuse me. So it turns out when I was a child, I had a bingy bank. A lot of kids have piggy banks, but mine was Ben Franklin, and the slot for the coins goes right in the bottom. Of course, Franklin was famous for the experiment that he did involving a key, lightning, a kite, and probably a servant to hold the string, because it was pretty evident that lightning was dangerous stuff. They already knew that it could cause fires and kill people. But he discovered the electrical nature of lightning and a bunch of other stuff too. He was a smart guy. As you all know, like charges, that is two positive charges or two negative charges, repel each other, while opposite charges attract each other. Pretty common knowledge. What you also know is that you can charge something, that is, give it an unequal amount of charge, by putting it in contact with something that is charged. For example, if you rub a balloon against your hair, the balloon will take on a negative charge. That means it'll have somewhat more negative charges than positive charges. And then if you bring it in contact, let's say with this little metal ball right here, some of the negative charge will leak off onto that metal ball, travel down the metal rod, and these are two leaves of foil, very lightweight, and they'll both travel out into that. So we'll have negative charges on both, and since like charges repel, these two things, these two leaves, move apart from each other. Okay, this device, by the way, is called an electroscope. Charging by induction is a little bit different from charging by conduction. It doesn't involve any direct contact. The idea is this. Let's suppose we have two metal balls touching each other and they're on stands that don't allow electricity to pass. Maybe they're on plastic stands. Okay? If we bring that charged balloon close to one of the balls, it'll attract positive charges toward itself. By the way, not really. That explanation will come a little bit later. And it will push negative charges away from itself. And yes, that is really in fact true. So you'll see that, let's say in this case, 5 negative charges get pushed to the right, leaving behind 5 positive charges. It used to be neutral. And so when we move the two balls apart, now the negative charges and the positive charges have been separated from each other. And when we take away the balloon, now they push each other apart and distribute equally around the balls. And now the two balls have charges. That is, the ball A has a positive charge and the ball B has a negative charge. By the way, you'll notice that they had the same amount of charge, just opposite kinds. Okay, that's charging by induction. That's called an induced charge. The law of conservation of charge says that in a closed system, the total charge doesn't change. Now, interestingly, the law of conservation of charge was developed by, yes, Ben Franklin, and there were some other people too. And if we go back to the previous slide, please notice that on the first diagram, the total charge is 0. That doesn't mean there's no charge. It just means there's an equal amount of positive charge and negative charge. They cancel each other out. You know, the positive charges are in the protons in the nucleus, and the negative charges in the electrons that are going around the outside of the atoms. Same amount of both. But if you look at diagram 4, we still have the same amount of both if you consider the whole thing to be just one system. That is, the positive charges and negative charges, count them up, they're opposites. We still have a total net charge of 0. That's what the law of conservation of charge says. The total charge doesn't change as long as we don't bring in anything from the outside world, like that balloon. The elementary charge is the smallest amount of charge that we usually deal with. The proton has one elementary charge. We could call that P plus or even E plus. Or the electron, which has one negative elementary charge. The amount of charge on the proton and the electron are absolutely equal. It's remarkable because it didn't necessarily have to be that way, but it is. And it's a good thing. It allows the universe to exist. The international system unit of charge is called the Coulomb. That's named after someone we'll come upon a little bit later. And it's a lot of elementary charges because electrons and protons are really, really small. So 1 Coulomb for a charge, for example, is 6.25 times 10 to the 18th power positive charges, or 6.25 times 18th power protons. That's an awfully big number. If you think of 1,000,000 protons, now take 1,000,000 piles of 1,000,000, you're all the way up to 10 to the 12th. Now take 1,000,000 of what you just created. Now you're up to 10 to the 18th, and then you want 6.25 of those. That's a lot of them. The other way of looking at it is 1 electron is negative 1.60 times 10 to the negative 19th power coulombs. That is, 1 electron is very tiny compared to a coulomb. By the way, if you multiply those two numbers together, see what you get. Try it yourself. So, conductors, and I've already talked about it, are things where charges move really easily. Salt water conducts electricity very, very well. Metal is a very good conductor, at least most metals are. Lead's not great, but iron is excellent. Gold is tremendous. Aluminum is great. Silver is wonderful. They all allow charges to move very easily. In a solid object, only the negative charges are free to move. And that's because the meaning of solid is that the atoms are not moving relative to each other. And you know what determines the position of an atom? That's right, the nucleus. And that's where all the positive charges are. So if it's a solid, the nuclei don't move, which means the positive charges don't move, but the negative ones do. And I alluded to that earlier. Insulators are substances that don't allow charges to move very easily. Plastic, dry air, rubber, dry wood. These are all examples of electrical insulators. By the way, there's something in between the two called semiconductors, things like silicon. And we use those to create integrated circuits and microprocessors and all that kind of cool stuff that's become popular in the last 60 years. So Coulomb's law, who's Coulomb? Well, this is Coulomb. His name is Charles Coulomb, French, as you can see, République Française. And you know what that thing is next to him up here? That's an electroscope, okay? It's also something called a capacitor. So he had a postage stamp that was made in his honor. And as you can see, he lived a long, long time ago. Anyway, it says the electrostatic force between two charges varies directly with the product of the charges and inversely with the square of the distance between them. And of course, don't forget that like charges repel and opposites attract. Now that's a really long sentence, but it just means this. It means if you want to find the force between two charged objects, you take some constant. What's the constant? It's that. We'll get to that in a moment. And multiply it by the first charge and then times the second charge and divide it by the distance between them. If you want that force to be measured in newtons, then the charges have to be in coulombs and the distance has to be in meters. And so that constant proportionality K, the Coulomb constant, is a very, very big number. 8.99 times 10 to the 9th power Newton meters squared per Coulomb squared. That's a funny looking unit. Because here's what it means. If we had two charges, each 1 Coulomb, and they were 1 meter apart, the electrostatic force between them would be 9 billion newtons. And if you're not familiar with the Newton, go back to earlier lectures, it's about 1/5 of a pound. So you could say it's about 2 billion pounds of force just for two 1 Coulomb charges a meter apart. So it's a good thing we don't have that much charge a meter apart. That's an awful lot of force. But it allows us to do computations on problems like this. Two charges are separated by 75 centimeters. Charge A is 30 microcoulombs and has a mass of 11 grams. Charge B is negative 20 microcoulombs and has a mass of 34 grams. What is the acceleration of charge A? If you think you can do this already, feel free to pause the video. If not, just keep on watching. My suggestion as a first thing to do would be to draw a picture. Notice that I made the distance between the two objects 0.75 meters instead of 75 centimeters. That's because that constant of proportionality, the Coulomb constant, has meters squared in it. And so our units have to be in meters. Charge A, let's see, I have that listed as Q. Q is the symbol we use for charge, is 30 times 10 to the negative 6, that's what micro means, coulombs. And the mass of charge A is 11 grams. I changed that to 0.011 kilograms. Charge B is negative 20 microcoulombs, so negative 20 times 10 to the negative 6th. And the mass of B is 0.034 kilograms. So how are we going to find the acceleration? Well, an important thing to remember is the most important law in physics, and that is the sum of the forces is mass times acceleration. And don't forget that both acceleration and force are vectors. And so if we can find the force between them using Coulomb's law, and we already know the mass, we can find acceleration. So let's find that force. Let's see, Coulomb's law says that the magnitude of the force is K, which is 8.99 times 10 to the 9th power, and I'll leave the units out because I've taken care of that up here. It's Newton meters squared per kilogram squared, or Newton meters squared per Coulomb squared. So we're good with that. Times charge 1, so that's 30 times 10 to the negative 6. Might be a little handy to have a calculator ready for this. Times charge B. Now we're taking the absolute value, remember, so I'll just write that as 20 times 10 to the negative 6th. If you hear some snoring in the background at any point, that's actually my dog, Rocky. He's quite sleepy. Divided by the distance in meters, 0.75. And don't forget to square that. That's the most common error that people make in this situation. Now just pop the numbers into your calculator and see what you get. I will do the same. And my calculator says that the magnitude of that force is about 9.59 newtons. Is that what you got? All right. Problem is that's not the question. The question asks for the acceleration of mass A. So the acceleration of A is going to be the force on A. Well, the force is going to be the same on both. That's one of Newton's laws. If B exerts a force on A, then A exerts a force on B of equal magnitude, opposite direction, divided by the mass of A. So that's divided by 0.011. So let's pop those numbers into our calculator. I'm doing that right now. And I get 871.7575758. I'm going to round that to two significant figures. So we'll call that 870 meters per second squared. Wow, that is huge. That's because those are actually really big amounts of charge, if you remember how big a Coulomb is on a really small amount of mass, and they're not very far apart. Interesting thing, at that rate of acceleration, it's likely to get closer and closer to B very quickly, and that'll shrink this distance, which will make the force even bigger, which will make the acceleration even bigger. Things happen when electricity is involved. That's how you work a problem. You list your variables, come up with the relevant formula, and then plug in the numbers and see what you get. All right, that's your introduction to electricity. See you next time.